Okay, let's move on. Today I would like to start a new chapter, which will be about the chemical reactivity and the reaction of complexes. So let us approach this topic from a very general point of view first, and let's think about what determines whether a reaction takes place or not. That is a question to you, and hopefully you all know the answer. So what determines whether a reaction takes place or not? There are basically two factors. Nobody knows the answer. Well, the first factor is the thermodynamics. So there has to be a thermodynamic driving force for the reaction to happen. And that thermodynamic driving force is defined by the free reaction energy delta G. So when delta G is negative, then we have a thermodynamic driving force for the reaction, and the reaction takes place. If delta G is positive, the reaction is not spontaneous and the reaction doesn't take place. Okay, so when is a thermodynamic driving force in delta G negative? So that is when the products are thermodynamically more stable than the reactants. So whether the reaction takes place is associated with the stability of the reactants and the products. So what is the other major factor? The other major factor is the kinetics. So even though a thermodynamic driving force for the reaction may be present, the reaction may still not happen because the kinetics of the reaction may be slow. The kinetics of the reaction is associated with the reaction rate, which is determined by the activation energy. So when the activation energy is high, then the reaction is very slow, even though the thermodynamic driving force may be large. So what property of the reactants and the products is associated with the activation energy? So that's with the inertness and the lability of the compounds. In coordination chemistry, these are complexes. So when our compound is very inert, then that means that the activation energy to cleave the bonds is very high, and all reactions are very slow. When the bonds are very labile and our complex is very labile, then the reaction rate is significantly faster because the activation energy to overcome the bond cleavage is significantly lower. Okay, so now let's go from this very qualitative picture to a more quantitative picture. So how well labile does a complex need to be in order to be considered labile, and how inert does a complex need to be in order to be considered inert? So when we have a labile complex, then there's a fast ligand exchange because the activation barrier to cleave bonds is very low, and we can quantitatively say that when the half-life time of a bond is smaller than 30 seconds, then we say that this complex has a low activation energy. So what is an example for that, for instance? So an example for that is the substitution of the thiocyanate ligand in penta-aqua thiocyanate, iron 2 plus by fluoride ligands. So this reaction happens very fast because the half-life time of the iron sulfur bonds is very small. So that means that in less than, in this case, smaller than 1 second. So that means that in less than 1 second, 50% of the iron sulfur bonds have statistically cleaved. Okay, so that means that the equilibrium will be reached very fast and the reaction is complete in a very short amount of time. So opposed to that, when we have an inert complex, then we have a much longer half-life time for the metal ligand bonds. We say the threshold is larger than 30 seconds. And then we say that this complex has associated with a high activation energy. So we can also see what is an example for this. So for instance, the hexaamine cobalt 3 plus complex is a pretty inert complex because the half-life time of the metal ligand bonds is larger than 1 day. So therefore, any ligand substitution reaction occurs very slowly, and the chemical equilibrium does not establish quickly. So in this reaction, the amine ligands get substituted by aqua ligands in an acid medium. Okay, now let's go to the question, which complexes are inert and which ones are labile? What properties do the metals and the ligands need to have to produce inert and a labile complex, respectively, in their number of factors to consider? So first, let us look at the D block metal ions. Certain electron configurations favor inert complexes and other electron configurations favor less inert complexes. So generally octahedral D3, low spin D4 to D6 because of high ligand fields strength and associated larger bonds, as well as planar D8 complexes tend to be inert. The probability is higher that other electron configurations produce a more labile complex. So in addition to that, when the metal is of a higher period, then the complexes tend to be less labile. You can actually understand this using the hard and soft acid and base concept that you have learned about. So we said that when a species becomes softer, then it more likely makes covalent interactions because the energy differences between the orbitals are smaller. So when the energy difference between the orbitals becomes smaller, then with a greater probability, a ligand orbital has a similar energy than that metal orbital, and then that leads to a more covalent bond, and that more covalent bond is then tends to be less labile. So another important factor is the charge. So the higher the positive charge of the metal ion, the less labile. So that actually connects to the previous point in the sense that when we have higher positive charge, then the covalency of the metal ligand bond tends to increase. This is because highly charged species tend to be unstable when isolated and naked, okay, just because of electron of charge repulsion within the species. And for that reason, that high positive charge needs to be stabilized by a covalent interaction with a ligand, which leads to electron sharing. So that electron sharing leads to greater covalency and in turn to a greater inertness. Another argument is just simply electrostatic. When we have a higher positive charge, then we have more electrostatic interactions with a ligand, and these stronger interactions then also translate to a smaller lability of the complex. Okay, so when we look at the other blocks and compare the lability of the other blocks, the D block, then we find that the S block is the most lable block, followed by the F block, followed by the D block. So S and F metals tend to make more lable complexes than transition metals that have d-valent electrons available. With regard to the P block, the lability can vary a lot between highly lable and highly inert. It depends on the exact circumstances, which metal we use and which ligand is present in the complex. All right, last but not least, also the ligand is of significant importance. So generally, when the ligand is a good leaving group, then a complex tends to be more lable. When it's a bad leaving group, the complex tends to be inert. You probably know the concept of the leaving group effect from organic chemistry. So a reaction proceeds more easily if the substituent is a good leaving group. Then also the reaction proceeds faster. And in analogy, in coordination chemistry, a reaction proceeds faster when the leaving ligand is a good leaving group. So this is typically the case when the leaving ligand is a stable species in itself. So that would be for instance true for a chloroligand, which can make a stable chloride ion. Okay, a bad leaving group would be, for instance, a methyl group, because if you want to make a methyl group leave, then you would either have to produce a methyl radical or a methyl anion, both of which are not very stable species. Okay, so now let's go from the kinetics to the thermodynamics and look at the stability of complexes. And let us look at what determines the stability of complexes. So generally, the stability of a compound, including a complex, is determined by the equilibrium constant K of formation. So the higher the K is, the further the chemical equilibrium lies on the product side, and the more stable that complex is. So the K value is directly related to the delta G value of the respective chemical reaction. So both are connected to this Van 't Hoff equation here, which you've probably seen before. It says that delta G is minus R times T times L n K. So that means that the larger K is the more negative delta G comes. All right. So, well, that equation here relates to this chemical reaction in its most simple form, in which we form a metal ligand bond from a metal and a single ligand, and then K is being given by the concentration of the complex over the concentration of the metal times the concentration of the ligand. All right. So K itself can vary over many orders of magnitudes, actually 35 orders of magnitudes. Therefore, often K is given as the decadic logarithm of the K value. All right. So now let's go to the question, what determines the stability of complex? And here we can apply a concept that we have previously learned, which is the hard and soft acid and base concept. So we learned previously that the HSAB concept can explain bond strength, and as such, it can explain the stability of molecules, and we can apply this idea now also to explain the stability of complexes. So here's an example. So you see here different log K values for silver complexes. You see that with amine, the silver plus makes a complex that is associated with a log K value of 3.30. With fluoride, the log K value is minus 0.17. With chloride, it's 3.08. And with bromide, it's 4.30. So obviously, the complex with bromide is thermodynamically most stable. The complex with fluoride is thermodynamically least stable, and the complexes with amine and chloride are intermediate. So you see that this aligns with what HSAB would predict about the stability of the complexes. So the silver plus is a soft cation. So we would expect that it makes the strongest interaction with the softest ligand, which is in this case the bromide anion. And accordingly, the stability constant K is the highest for this combination. Okay, so fluoride is the hardest of our ligand. Therefore, we would expect the lowest constant of formation. And that's also what is being experimentally observed. And well, NH3 and Cl minus are approximately in the middle and have approximately the same stability constant because of their similar hardness. Okay. Then let us have a look at the stability of multi-ligand complexes. So a complex cannot only be attached to one ligand. There can be 2 or 3 or 4 or 5 or 6 or even more. So how does the stability constant change as we add more ligands, and why? So the addition of each ligand is associated with a separate chemical equilibrium, and for that reason, there is a separate constant of formation associated with it. So for instance, we have a complex of type Ml4, it's 4 ligands, generic ligands. Then in the first step, we would add the first ligand to the metal, and that would be associated with a stability constant, which would be given by the concentration of ml over the concentration of m times L. Then to this species here, we can add a second ligand, which would form a complex of the type Ml2. So this reaction here would be associated with another equilibrium constant, K2, which would be given by the concentration of the complex Ml2 over the concentration of the complex Ml times L. So we can now add another ligand to this complex here. So this would add a third ligand. According to this reaction equation here, Ml2 plus L gives Ml3. And the associated equilibrium constant, K3, would then be Ml3 over Ml2 times L. And finally, we can add our fourth ligand to Ml3 to give Ml4. And that would be associated with the last equilibrium constant, K4, which is given by the concentration of Ml4 over the concentration of Ml3 times L. Okay, so now what can be said about the relative order of these equilibrium constants, K1, K2, K3, and K4? And the answer is that the equilibrium constants decline from K1 to K2 to K3 to K4. So can any one of you imagine why that is? Or maybe you also know why that is from the previous more introductory course. So the answer is this is a statistical effect. Okay, so K1 is larger than K2, is larger than K3, larger than K4. Okay, and for a general complex MLN, K1 is larger than K2, then K3, then Kn. So now the explanation is statistically because the number of available free ligands decreases with n. Okay, so now you can understand this when you consider that in order of the complexes to form, the metal needs to collide with the ligand. Okay, so now as a metal ligand forms, less many ligands remain in the free solution, so that the statistical probability that a ligand collides with the metal to form in complex with even more ligands is statistically smaller. So as the reactions proceed from 1 to 4, the number of available ligands in the free solution declines, and therefore there's a statistically smaller probability that the ligand can connect to the metal through collision. Okay. So now what is the overall stability constant? When we sum up reactions 1 to 4, then the overall stability constant is nothing else but the product of the individual constant. And when we have a more generic complex, MLN, then the overall stability constant is nothing else but the product of the individual constants from K1 to Kn. Okay, now there are exceptions to this, and these exceptions are also interesting because when you measure such exceptions experimentally, then that indicates that there's a major change in electronic structure as more ligands are being added. And I would like to talk about a few examples related to that. Okay, so in the first example, we have here an hexa aqua iron 2+ complex that reacts with a bipyridal ligand. And in the reaction, two of the ligands are being replaced by the bipyridal ligand. Remember, the bipyridal ligand is a bidentate ligand with two end-donor atoms. Okay, we can measure the equilibrium constant for that reaction to happen. And we'll find that log K is equal to 4.2. So then we can add more ligand and replace another two water molecules from the complex to give a new complex. So we'll start out with this one here. That would be the tetra aqua bipyridal iron 2+. Add a bipyridal ligand to give a diaqua bis bipyridal iron 2+ and two free water molecules. So when we look at the associated equilibrium constant with this reaction, we'll find that it is 3.7. So this is what we would expect. There's a decrease in Kf as we go from the first reaction to the second reaction. So now let's do a third reaction and substitute the last two water ligands by an additional bipyridal ligand to give this tris bipyridal iron 2+ complex. So we can again measure the equilibrium constant, but now we see, big surprise, the equilibrium constant is much higher than the other two. Now this indicates a major change in electronic structure, and in this case we have a transition from a high spin complex here for these two reactions to a low spin complex. And we transition from a high spin complex to a low spin complex because our bipyridal ligand is a strong pi acceptor, and because of the pi acceptor properties, our delta O increases, and upon the third substitution, our delta O is large enough that the spin pairing energy is being overcome, and we transition from a high spin complex to a low spin complex. So we have a significantly different electronic structure in our low spin complex, and therefore we see an exception from the log K exception in the log K value. Okay, one more example. So here in this reaction, we look at the substitution of water molecules in octahedral mercury complex by chloro ligands. So in the first substitution, one chloro ligand substitutes 5 of the 6 aqua ligands here to give this penta aqua chloro mercury plus complex and one free water ligand, and this reaction is associated with a log K value of 6.74. Okay, Now, when we substitute for a second time, then we go from a penta-aqua complex, and I actually just see that I forgot the one chloro ligand here in this complex, so this one has been forgotten. And then as we add as the chloro complex, we substitute one of the 5 aqua ligands by another chloro ligand. So we have 4 left and 2 chloro ligands in addition. So this is associated with a log K value of 6.48. So now if we do this for a third time, and we want to substitute the a third aqua ligand, and again here the 2 chloro ligands are actually being forgotten. So please add these here, and I have to correct this on the slide. Then in this case, we change the coordination number. So we change the coordination number from 6. So this should actually be 6 here because we have 4 aqua ligands and 2 chloro ligands, to 4, where we have now 3 chloro ligands and 1 aqua ligand. So this is a change of coordination number. It's also associated with a significant change in electronic structure, and therefore our log K value is not what we would expect. So it is indeed smaller than these two, okay? But the decline is actually too strong in order to be statistically significant or just produced by statistics. We can only explain this when we assume a major change in the electronic structure, which is in this case a change in the coordination number. All right. So here's just a summary. We have too low of a value to be a statistical effect, and the explanation for that is that change the coordination number from 6 to 4. Okay, now let us look at the thermodynamic stability of chelate complexes in particular. So chelate complexes have the property to be thermodynamically significantly more stable than complexes with monodentate ligands, and we call this the thermodynamic chelate effect. So what causes this effect? And the answer is entropy causes it. Okay. So there's an increase of entropy when 2 or more monodentate ligands are replaced by chelating ligands, and we can easily see this when we compare the number of species on the left side of the equation with the number of species on the right side of the equation. So an example for that is here. So here we have a hexamine nickel 2+ complex that reacts with 3 ethyl and diamine molecules. We form a tris ethyl and diamine nickel complex and 6 ammonia molecules. Now you can count the number of species here on the left side, and here we have 4 species, while here on the right side we have 7 species. And 7 species just have more degrees of freedom, and therefore on the left-hand side, also on the right-hand side, we have a higher entropy in comparison to the left-hand side. So the exact entropy gain is actually 88 joules per Kelvin. And more in this entropy gain explains the high thermodynamic stability of the chelate complex. Okay, now in addition to the thermodynamic chelate complex, we also have what is called a kinetic chelate complex. So that kinetic chelate complex leads to the fact that chelate complexes also tend to be more inert, and for that reason, their substitution occurs at a smaller rate. And this is illustrated here, in which an ethylene-diamine complex is bonded to a metal via two metal-nitrogen bonds. So now as one of the bonds cleave, due to the fact that, well, the first donor atom is still attached via these carbon bonds and the second donor atom to the metal, there's a greater probability that this nitrogen donor atom remains in the proximity of the metal, even though the metal bond is cleaved. And that actually increases the statistical probability that it reattaches and the reverse reaction occurs. So in sum, the bond cleavage is smaller. So now the possibility to reattach the metal also makes it less likely that both metal ligands can cleave. So therefore, the follow-up reaction in which a free ethylene-diamine molecule is formed is therefore also slower. Okay. All right. Now let us go from the inertness, lability, and thermodynamic stability of complexes to the mechanisms of ligand substitution reactions. So according to which mechanisms can they actually occur? There are a number of possibilities. So the first possible mechanism is the so-called intimate mechanism, and according to this mechanism, and the second possibility is the so-called stoichiometric mechanism. So when we have an intimate mechanism, then we do not form an intermediate, we only have a transition state. Okay, so as we go from the reactants to the products, we go to one maximum on the reaction coordinate. So in contrast to that, when we have a stoichiometric mechanism, then we have the formation of an intermediate. So that means that we have an additional local thermodynamic minimum on the reaction coordinate, and we have two maximum that represent transition states. Okay, then there are several possibilities how we can realize a stoichiometric mechanism. Yeah. So the reactions occur according to the principle of microscopic reversibility. That means that the reverse reaction follows the same reaction coordinate as the forward reaction. Just to add that. Yeah. Sorry, I forgot another point. So how do we define the activation energies for these two mechanisms? So for the intimate mechanism, the activation energy is defined as the energy difference between the transition state and the energy of the reactants, okay, whereby the free reaction energy is the energy between, is the free energy difference between the free energy of the reactants and the products. Okay, this would be this one here. Okay, for the stoichiometric mechanism, the free energy of the reactant is defined the same way, but now the activation energy is the energy between the first maximum here on the reaction coordinate and the free energy of the products. Okay. All right. Sorry. Now, as I said before, we can realize these stoichiometric mechanisms basically two ways, either through a so-called dissociative mechanism labeled D and an associative mechanism labeled A, D and A respectively. So when we have a dissociative mechanism, then our reactant ligand first loses a ligand to form an intermediate which has a lower coordination number, and then the new ligand is being added and the product is being formed. Whereas when we have an associative mechanism, then first the new ligand is added and the intermediate is of larger coordination number, and then that intermediate loses a ligand to form the product. So we only talk about dissociative mechanism and associative mechanism when the intermediate is clearly detectable. And that's the case when, well, that thermodynamic minimum here is fairly steep. However, or fairly deep, not steep, but deep. But often it is too shallow so that the intermediate is experimentally detectable. And when no clear intermediate is detectable, then we call this an interchange mechanism, and that interchange mechanism can either be IA or ID, depending on whether it's rather associative or dissociative. So that means that overall, we can have everything between associative, IA, intimate, ID, and D. Okay, so now how can we distinguish between a more associative and a more dissociative mechanism? We can do this by first thinking about what is the rate limiting step for the associative and the dissociative mechanism respectively. And for the dissociative mechanism, the dissociative step is the rate limiting step, because we first have to go steeply uphill in free energy, okay, to form our intermediate, okay. Once we have formed the intermediate, we only have to go up a little bit uphill again until we form the product. Whereas for the associative mechanism, the opposite is the case. We first have to go strongly uphill, strongly uphill, when we want to add a ligand, here to form our intermediate with higher activation energy. And after that, we only need a little bit more energy in order to lose our ligand and to form the product. So now we can use this property in order to distinguish between DID and AD. So in particular, if the reaction rate is strongly dependent on the identity of the new ligand, then it's rather A or IA. When the reaction rate is fairly independent on the new ligand, then it's probably a dissociative mechanism. And this we can actually see from this example here. So for instance, here we have ethylene, so a diethylene triamine complex with platinum and a chloroligand attached, and we can substitute that chloroligand by an iodo ligand. And we can do the same reaction also with bromide and substitute the chloride with bromide. So in this case, we see that the rate changes by the factor of 100, and that indicates that we have an associative mechanism or an IA mechanism, because we first need to go energetically strongly uphill to add the new ligand, and therefore it strongly depends on the ligand how much we have to go uphill to form that intermediate. All right, so what other factors determine, so what factors determine whether we have an associative or dissociative mechanisms? So generally, high coordination numbers lead to large steric crowding and they favor D or ID. Low coordination number have little steric crowding, and then more likely we expect an A or IA mechanism. So this is what I wanted to say about reaction mechanisms. We have an other exam coming up next Tuesday, not this Tuesday, but Tuesday thereafter. So all course material taught up to today will be subject of that exam. All other course material, which will now be on organometallic chemistry, and that will be the last bigger chapter in this course, will not be on the exam, but it will be part of the final exam. So with this, I just stop the recording.